Okay. Okay. I think we're good now. Whew. Sheesh. Last minute technical issues, you know? When you sit down, you pop everything up and everything pops off. But we're here now. Welcome back. My name is Agent Ultra, and I'm here to program for you tonight. And for me. So let's see. On this stream, I basically program in a language called Haskell for the most part. And we've been working on a little project for last month or so to learn about wave function collapse and implement it in Haskell. And yeah, welcome. So let's get everything set up. I'm gonna bring up my editor here. Everything going. We'll dive into the code. So if this is your first time tuning in, welcome. It's nice to see you. I am totally amenable to backseat programming and chatting and whatever's. Distractions are good. If you want me to stop and explain something, feel free to ask questions. I'm terribly happy to do that. So happy when people ask questions. Okay. So, without further ado, let's jump in. Let's get going. Let's get some. We're going to go in algorithm wave function collapse. Now, I believe we left off with... We had a bunch of stuff for entropy, choosing a cell, collapsing a cell, running a wave. We set up our wave state with our entropy list. Yeah, we got the min heap here. So, whoa, the min heap. This is how we're keeping all of our next cells to collapse, because we're supposed to choose the cell the minimum entropy. So entropy cell here is keyed off of each cell's entropy in the min heap, and so whenever we pop off of this, we always have the lowest one. We added a cool little trick thanks to the Gridbugs tutorial on this stuff. We add a little bit of randomness to each entropy cell before we pop them into the heap there. Calculating the entropy of it, yeah. Alright, right. So we make a cell, that's where... Take the possibilities, calculate its total weight, sum of weight, log weight. Alright, possibilities. There's a list array from the pattern result max index. Where they're all true. All things are possible initially. Everything is permitted. Let's see, remove possibility. Okay, cool. So let's see. When we set up, I think maybe we have to set up this the min heap first. Choosing a cell. Oh, add entropy cell. No, let's see. Entropy cells. The wave state entropy list. Oh yeah, see, we make the rad noise. We add the create an entropy cell, insert it into the heap, and we add the updated heap to the state. Okay. So we have add entropy cell. I think, yeah, maybe we need to set up the grid, the initial entropy cells. Yeah, okay. We have that definition. We haven't used it yet, so yeah, we totally need to. Okie doke. Okay, yeah. So run wave, I'm guessing. I think run wave is. I'm guessing. But I'm reading past me's code, and it's been a couple of weeks. So run wave is where we initialize, take the initial wave state, a function in that wave state, and produce a grid. I think this is going to be like our top level function for running the algorithm. So in here, what do we call it? We call exec state wave on init state. And wave oh, wave is passed into us. Okay. So, true set to be so. No. Okay, so we actually need our top level, set up our top level kind of function, I guess. So this is just like running the wave state. Okay, so whatever our wave function should be. It's called a wave function collapse. It's a state of wave state of A. Okay. So in here, when we get our wave state, that means our caller is going to set up our initial grid, our frequency hints, our standard generator, and all of that stuff. Oh, even our min heap, we have to set that up too. Really, we should be initting the wave state here. All right, all we need to do to initialize the wave state is to get the size of our grid that we want. Our input. Well, actually, that's kind of determined. No. Yeah. The size of our grid we want. The frequency hints we get from the first part. Initializing our standard generator and the min heap. And yeah. Why don't we do that? Unlock wave state. There's a wave state. We're going to need the size for the grid, so we'll int. Grid width, grid height. Just like this. Okay. Now we need to know, we need to turn up wave state, so let's do that here. Wave state grid. We're going to need our frequency hints passed into us. And freak hints. Freaky hints. Standard generator. Let's see, we could have one passed into us as well. Or I think we can make one. So we might want to do this in IO. System.random. Now we want a pure generator. I think standard generator has to be an IO. Or we have to give it an integer to construct it with. Okay, so we don't actually need to be in IO. So let's do that. That'll be nicer. That'll be our seed. Wave state gen is muck standard gen, unique standard gen from seed. Another cell entropy list. Something there. Okay, so then we just need the grid and then the entropy list. The grid is pretty easy to construct. We have this constructor here. Word. Oh, we need pattern resolve in order to call this constructor. Oh, that ties things together, doesn't it? Frequency hints. Guess it kind of makes sense. Yeah, so we'll have to get the pattern result passed into us. Although, what it's generating frequency hints here on the pattern results instead of getting those passed in. We're already going to have the frequency hints passed in. So this should probably be changed. Yeah. So instead of putting in the pattern result, we'll just give you the frequency hints. Here, put it over there, and we don't need the OR to A anymore. Yeah, we're good there. Super duper. Okay. Let's see, what else do we need? Pattern result. And we need pattern result because of make cell. Why does make cell need the pattern result? Because it needs the possibility. It needs to calculate the possibilities. It's almost like I want to do this. No, I need to make it smaller. Okay. Get rid of that hunk. Yeah, there's no sense calculating the frequency hints twice. We need them at the top level state. So I feel like muck grid is just tying too many things together here. We need to split it apart. And then, okay, I'll take a quick little break here. I think I might have forgotten to notify some channels about the stream. Hang on a second. Wow. Okay, back, just notifying. We're live. Okay. Okay, yeah, so I think I need to split that apart for make grid. I guess we do need the pattern results in order to call make cell to construct make cell. Right, because we need to calculate all the possible patterns. And we need the max index, which comes in the pattern result. Of course, this is going to be used internally, so we don't really have to pass the pattern result here. We could just pass in that index. We could do pattern results. Okay, I think we're going to need the ORD instance on that A for the heap stuff. And then if we went this route, we're going to need to let bind the frequency hints. Pop those over there. And then we calculate frequency hints here. Just from the pattern results. Pattern result patterns. Okay. Oh yeah, we need to get rid of the IO here. Bang. Okay. Now grid. Make grid, my friend. We could go to the frequency hints. Here. Pop those in there and bring you as a parameter. Okay, then everything kind of slots together a little bit. Okay, so then we have to use our grid width and grid height in order to create the initial grid, and then we got to fill the entropy list. All new grid. But these should be word, so they fit into grid. Width, grid height. And then we need pattern results and frequency hints. Cool. And then our entropy list. I think actually we're going to need to bind the grid because we're going to need to go over all of the cells in it. Yeah. We'll just pop that up there, there. We're going to do some function over after getting the grid, something with the grid. Yeah. Grid. Get cells. Yeah, we're gonna call get cells. Ta-ta, ta-ta. Okay, so now we have a function from an array in of cells to heap. See, we're gonna fold over those into the min heap. Yeah, that's what we're gonna do. We'll start off with an empty min heap. Heap dot empty. Maybe. Okay, cool. So then this function has our heap accumulating a cell, returning a heap. So that's just heap dot add. And maybe it's insert. I don't remember. That's not heap. Insert. Yeah, where's our heap library? Data.heap. Split merge, no. Construction. Okay, it is insert. Oh, it just takes item as the first element. Okay, so we just need to flip this around. We expected to sell heap to heap. Actually sell heap. Okay. Okay, so this means they wanted to heap heap. The actual is a heap.heap to heap.heap. into the heap T. Okay, okay. So insert here wants us to do it inside this kind of heap. I think the T means transformer. Heap T here. Okay, so our fold isn't necessarily going to work in there. Interesting. And we put a hole here. Let's write it out. Call it where. Call it add cell. That. We'll take the type. And here, just straighten things out a little bit. Okay, not bad, not bad. This hole is down here. Get rid of that, yeah. Okay. So then I should be able to replace this with min heap. Entropy cell. Yeah. Okay, cool. And then this one too. Okay, at least a type check so far. Accumulating heap, our cell. Okay. So we have a cell. We need an entropy cell for one. How do we make an entropy cell? All right, we have actually a function for that. Add it to the wave state at least. Yeah. This is why we have this function, because using the noise generator, right, we're actually going to set off our, because we need to add the noise to each one. So what I think we should do here is initialize the entropy list to, in our make wave state function, to empty, and then when we start the algorithm, we're just going to have to remember to call some kind of initializing function to initialize the entropy list. Because like if we fold here and do that here, we have to take a random generator with us. Like we could, I guess we could do it here. The result of calling our kind of function for generating this is going to have to return the final value of our generator and then add it here into the wave state, you know what I mean? Let's try it. Let's try it. Let's see what it goes. There it goes. Build entropy list. Entropy list. We'll call it entropy list. Build entropy list. Build entropy list is going to take our generator, which is going to be mux standard gen seed. Entropy and gen prime. So we'll have to return a tuple of the entropy list generated and the final generator state. So we pluck that in here. And build entropy list then is going to have to take the generator. It's going to have to take, let's see, the grid array. Of the grid. Yeah, something like that. Build entropy list. Alright, we give the type. We have standard generator of int, I think. And we have an array of word. Entropy cell? No, of cell. That's going to have to take our initial heap. So it'll be a min heap of entropy cell. And then that's going to return our tuple of min heap entropy cell and our standard gen int. There. Build entropy list. Oh, what does it actually want? Do the old trick. Oh, it's just standard gen. Okay. Interesting. Pop that over there. And heap entropy cell. Turning cell, yeah. Okay. And step in. Just make it a little more readable. Okay. We could do it recursively, something like this. We're gonna build helper function. That's basically, really, let's convert the array to a list. I'll make build entropy list. And array Elms? We just need the list of cells, right? Okay, I think we should be able to do this. Okay, there's our generator. There's our list of cells if it's empty. Then we have our accumulating heap. And this should be the accumulating heap and the generator. Otherwise, we have a generator and we have a cell and some more cells. And we have the accumulating heap. Okay, now this probably wants to be in the this heap T thing. Hopefully this will work. Okay, so first we're going to need a random value. Ran between. Right, noise, rand noise. Uniform R between 0 and 1. Oh, uniform R, that's right. Okay, this will be uniform R of our generator between 0 and 1 as a float. Okay. Okay, so in this hole, we have heap T, yeah, our tuple. That's kind of what we expect, right? Oh, so I'm supposed to get some gen. Yeah, then we get a noise and our gen prime. Okay. Cool. And then what we need to do is we need to insert our cell, our entropy cell, into the heap. Like this, I think. Need item. Alright, it's gonna be our entropy cell. Alright, entropy cell is take something. I don't know if I remember I put it as a tuple or there. Float cell. Okay, so this should be the entropy of the cell plus the noise. Okay, entropy is just a function there. Entropy of cell plus noise. Cell. And then the heap's the accumulating heap. Okay. All right, so accumulating heap prime is our heap. That's good. Okay, so then we can continue building the entropy list. All right, with our gen prime. And the remaining cells, and our newly updated heap. Okay, I've just got some mornings there. Okay, and then for this, we just need entropy. You need gen prime. Oh, that's where it's overshadowing. Okay. Call it entropy list. And there we go. Sweet. Okay, so that's a function for initializing the state. We give it the pattern result. We give it the size we want for the grid, the seed to initialize with, and wave state. All right, we generate the frequency hints from the pattern results. We create the grid with the pattern results and the frequency hints, then generate the generator, build the entropy list by iterating over all of the cells in the grid array, accumulating them into the heap with a little bit of noise and stuff, then return gen prime back, yeah, okay. It's okay. Not bad. Pull that over a little bit. Pull this over a little bit. Okay. Ah, let's commit it. All right. Make wave state. Initialize all the things. Okay, so now that we can initialize the wave, we can make a wave state. And now we can move on to the next part, I think. Let's get our builder going. We'll use the test runner. Fast, file watch. Boom. Move on, something build. Oh, for some reason I'm not going to get that type error in here, but I'm getting it down here. That's interesting. Oh, that's in the spec tests. Okay, okay. Ah, yes. Okay. We changed the type of make grid, I think. Yes, so that makes sense. Spec. Let's pop over there. Oh, right. Make grid. Yeah, yeah, that's right. Okay. So we want the word as the size. That's the same as before. Oh, we pass in the frequency hints. Yeah. Frequency hints. The pattern result. Pattern result patterns. Okay, that all compiles again. I saw a quick little warning. I think it's just the usual ones. Oh, wait, uninitialized fields of wave state. The wave state entropy list. We don't really care about the entropy list in here. We're gonna need heap.empty. But that means I think we're gonna have to update the package to add heap to tests. Add the dependency, and then we have to import it. Let's go over here, import heap, qualified as heap. Post positive, sorry, post positive. Here it comes, it's coming back again. Qualified. Right. And that's wave state cell entropy list. Okay, there we go. That's better. Tests. Okay. Just quickly squash that down. Yeah, we're good. Okie-doke. Okay, so now that we have the wave state, we can initialize it. When we run the wave, when we run our wave function, let's do it here, just as I was going to before. Let's be a state, wave state, unit. Okay. So I believe we have like a kind of a little bit of a spec here. So this has to go down here. Alright. Yeah, so while they're uncollapsed cells, we got to choose a cell with the lowest entropy, collapse it, picking a pattern from the possible patterns, and then we're gonna do the propagate stuff. So we already have, I think, all of this. We just gotta start putting it together and propagate. Well, I think maybe I want to save wave function collapse as the top level entry point name for the algorithm, because I want the thing to tie together all the processing that needs to be done. So we'll call this collapse wave. Okay. All right, so guess the while part. How do we want to do the while loop? Maybe controlled up monad has something for us. Don't want necessarily to repeat forever. I suppose one way we could do it is we could have our conditional here. When there are collapsed, when everything's collapsed, do something. And so check collapsed. No, we want to check the whole grid is collapsed. We can check with the wave state grid. Or we could have like a sentinel value maybe that's like, we're going to keep a count in the state of cells, and we'll just decrement this counter every time we go to collapse, maybe? That way we don't have to keep querying the grid if it's fully collapsed or not. Kind of like how we cache some of the entropy calculations in each cell. Remaining cells. An int a jar. So then we have to update our make wave state to be well, the grid's going to be the width times the height. So the wave state remaining cells initially will be that. Oh, yeah, to integral. Or, sorry, from integral? From integral. Yeah, we could also make it a word. This won't go below 0. Okay, which means we need to update our collapse at. And so we update the state here, and we decrement. wave state remaining cells. I kind of want lenses now. I'm getting this code's getting close to the point where we might want to introduce lenses, especially the MTL lenses. If it gets any more annoying, then we'll get there. Okay. So then our when condition, we have to get our state. And when wave state remaining cells is greater than 0, we'll do something. And we will... What we do? What will we call it? Collapse more? Propagate? Propagate collapse? And we have to import control.monad. Okay. Sick. Propagate, collapse. Let's do it. Okay. So, we gotta get our wave state. Actually, we actually... just do gets wave state cells. Do that, get there. Okay, cool. We get our state out. Then we have to choose the cell with the lowest entropy. Well, that's going to be pretty straightforward for us now. So our next cell, right, it's going to be a heat. Get pop. What do they call it? What do they call it? Split, merge, null size, view for the head. View head. That's what we want. What's up, Chexor? How's it going? And welcome to the stream. Super Quantum. I have been following a guide, but we're getting to the interesting part of the algorithm, and so I'm taking a stab at just doing it without peeking ahead. But then I'll compare later on my implementation if it doesn't quite work. So we're doing wave function collapse. It is actually a procedural generation algorithm. It gets its name from the physics concept. Which kind of helps. I guess it kind of helps people understand it. The general gist of it is, well, that it's like a forward propagation solver algorithm. Yeah, it's pretty hard. Yeah, so this is the guide I've been using, grid bugs. This one's a Rust implementation. There is a GitHub with the main algorithm description. The general gist of it is you give this kind of input image as a sample image. You do a bunch of pre-processing on it, and then the algorithm can generate a much larger image that has a lot of self-similar features. Yeah, it's often used for, yeah, exactly, dynamic level generation or like texture generation, funky procedural art, all kinds of stuff. People have used it to generate poetry, and all kinds of things apparently. So we're learning about it, and we're implementing it in Haskell. Yeah, so we want to view the head to get the next cell into scope. It is pretty cool. I think I chose the most difficult variant to implement. It can be. Yeah, this particular variant is difficult, so I would say. So there's a few different ways of doing it. The general idea, though, is that like you have like a for constraint propagation algorithm. Let me pull up my pen. You basically have a bunch of data, variables in some thing, and those variables are initialized in the state where they could be all possible values in your problem space. And you have a set of adjacency rules or constraints. And those constraints tell you how those variables can fit together. And so when you pick a value for a variable, you then propagate those constraints outwards to the other attached variables. Right? So in the simplest way of implementing this, the simpler version of it is just to use tiles. Like straight up tiles. So you might have like a grass tile and a water tile. We'll just use like pink and yellow. Right? And the rules might be that pink can only appear next to yellow. Right, and yellow, or it'll probably be more interesting if we had more colors, but... So if we picked pink for this one, that means that of all the colors, right, we propagate out that change, these next tiles would be yellow and yellow. So if you had like a level, you know, you could say like coast can only appear next to water, or whatever else, green on the other, grass on the other side of it, but water on the water side of it. And you can kind of arrange your tiles that way. Right, in that kind of mode, in implementing that algorithm, I think it's a little bit simpler because you can just write the adjacency rules for those tiles directly in code, or even in like a data structure or whatever, and or like a file, and parse them into a data structure directly. Whereas we do, in this version, we're doing pre-processing on an input image. So all you have to give is that kind of bitmap as your input. And then we do a bunch of processing to slice these up into subpatterns, all overlapping subpatterns. And each of those subpatterns actually generate the adjacency rules. And then all this other stuff that we've learned about so far. In order to extract these kind of like subpatterns, which are then used to generate the adjacency rules, and you can build the bigger images from those. So it's a little bit more tricky because you have to generate the adjacency rules, that sort of stuff. And I think one of the things that really... yeah, it is pretty mind-bending, I guess. I think one of the things that really made me go like, ugh, every time I tried to implement it in the past is that when you do this version of the algorithm, laying out these tiles, what I'm calling patterns, when you're laying them out into the bigger image, you only need to output the top left pixel of that subpattern into a given cell or pixel in the output image. I was like, what? I assumed it would be like the set of pixels in the pattern you'd be kind of stamping in, but it's just the top left one. And it's because of the way the adjacency rules work when you pre-process them and develop this overlapping method that you get the rules of the algorithm guarantee that you'll get the self-similar regions. Am I going to apply this to a bigger project? You know what? I don't know. I'm just doing this for fun and for learning. It was just something that seemed relatively straightforward to implement in Haskell, and that's kind of what I do this stream for. Showing people that you can build real software in Haskell. It's not just for writing white papers and doing physics and stuff. So, I don't know, maybe we'll use it and we'll build a game. We've built games on this stream in the past. We'll probably, if it turns out like a decent algorithm and we can make it fast, maybe we'll even put it up on Hackage for other people to use, if there isn't one already. And then maybe we'll make a game with it? I don't know. Could be fun. But I wanted to do this in like the kind of the dumb, simple way in Haskell first. Probably build a DOM tree with it, yep. For sure. Especially that tile-based, the rule-based one, the more kind of low-weight-based one. People have done it for like generating 3D models and cities and stuff like that too. Alright. So what's the problem with this one here? Oh, right. That's not a state function. Silly me. That's just it. Okay. Okay, view head. What does view head return again? Maybe item. Alright, because there might not be. Okay, so if we propagate the collapse and there... If we don't have a next cell to choose with the lowest entropy, that either means that we're done, or possibly that we've encountered a contradiction. Our contradiction condition is when a cell has no possible patterns to collapse to. Oh, no, that... Yeah. That's when it has the cell itself has no possible patterns to collapse to. If we do pick a cell off the heap and the heap is empty, yeah, I think that means we've gone too far, because we would have done that in the previous step. And if we we still are continuing in this propagate collapse part, after we pop this, then we're not in a good place. That should probably be an error. And this will be wave state cell entropy list. For expedience sake, I'm just going to leave this as like a crappy exception. Probably add a little to-do for me to clean up later. Okay, probably because we weren't really an acceptee, I guess, around the state, but... Okay, so we just have a cell. Then we're good. Alright, so then we have to collapse it. Our heap is the entropy cell. Ooh, the actual cell. We just need the cell coordinates there, I think, maybe. Which is going to mess up all the code we just wrote. Dang. Right, because I have this handy-dandy collapse at function that we wrote a while ago. That just takes the cell index. Okay. There's no way around it. We have to do it that way. I think that's the better way of doing it. We probably shouldn't be storing the cells in the heap. We store them in the grid. Okay. We'll have to get back to this hole. We'll leave it undefined for now. We'll go fix that. And then I think we might be running a little low on time, yeah. So we might have enough time to fix that. And see if we can get back to this. Create a little work in progress commit. Add collapse wave. Okay. So our entropy list should be our cell indices in the grid. That's our ord instance for the entropy cell type. And then that's our min heap. Okay, so that's going to affect the construction build entropy list. We don't want the list of cells, we want the list of indices. I'm making it as a library. Yeah. So this turns out good, maybe we'll put it up on Hackage. If there isn't one already, like I was saying. Although I'll probably include like a demo app with it, so that you can just fart around with it, try it out. All right, so we're gonna do it the stupid dumb way first, and then try to make it as correct as possible, and then we'll use that as a test oracle for the performant one, which we'll try to use a lot of. We'll probably end up using mutable arrays and stuff like that, mutable vectors to implement the grids and all that stuff. Okay, okay. That is, unless our pure one is fast enough. We'll see. I highly doubt it, though. Okay, so instead of the cells, we want the indices. So instead of array elements, we want the array indices. I don't think that's the right function. One of these days, I'm gonna have data.array locked in here, and I won't have to worry about it anymore. Yeah, it is indices. Oh, look at that. Amazing. Yeah, the list of indices in ascending order. Perfect. Perfect. What's wrong with grid cells? Yeah, so then we have to change this to int. And then I'm just going to make this a little bit more clear by renaming it to cell X. We do need the cell because we do calculate the entropy in order to add the randomness. Okay, that's no problem. So we'll just get we'll get them both. We'll get the association list. And that changes this to cell. Brings that in scope. Okay, no problems. Are we happy yet? Not quite. Why is it popping over here? There we go. Okay. Oh, I already have a choose cell function. Ha! Hilarious. Okay, cool. I'm catching up with myself. It's been a couple of weeks since I've been working on this, so hey, cut me some slack here. Thanks, past me. And I already did the air handling. Cool. Cool, cool. Alright, so here we get the cell X. Right, and then we're going to need it to have a different function here that uses cell X. This should return the cell index. Probably make that a new type. Okay, so collapsed. That's a fine function to have. I've check collapsed. Not this one, nope. Collapse at is collapsed at. Probably we should have. Should it be int state wave state bool. And then do. So then we're gonna have to do cell collapsed. Is collapsed at cell X. Then if cell is collapsed, choose the cell or pure cell index. Okay, yeah. So when we go to choose one, we look at the heap list of entropy cells. Should be able to get here. We get the one off the list, off the top. And we, instead of using view head, we do use view here because we use, I guess, remaining entropy cells in order to modify the state. So we don't, yeah, okay. And then check if it's collapsed. If it is already, then we go to the next one. Or we choose again until we get one that isn't. Okay, cool, cool, cool. I think that's how it's supposed to work. Okay. Do we have any more type errors? Yes. Wave state. That's not good. Okay, so we have to implement is collapsed out still. What's the other one? Yes. Add entropy cell needs to be worked here. I don't think anything calls this yet. So this will be a cell index and a cell. We're going to be passing these around together. No. It can just be the cell index, because we can get that out of the grid. I'd look at get cell. cell at. Sort of. Sort of. So this will be cell X. Well, it's a maybe. We're gonna have to case match on it, which is another sign I'm gonna need. Probably gonna need error T over state, or accept T or whatever you want to call it. We need to add exception handling here. Not really exception handling. I wish they'd come up with a better name. Probably alias it or something easier, but it's called accept T. Yeah, but it's really for errors. Errors is values, just with an amount. Kind of like exception handling. Anyways. Yeah, so we need to get the cell from the grid in our state. Like that. And then cell will be fine. Except this needs to be X. Yes, I believe that's the official one, I think, too, right, Checksar? Yeah. That's the original, the OG. Alright, so with like a little blending function, we should be able to implement an animation like this, or like a little, as our little demo app. That's what I'm thinking, like, we'll make a little Qt kind of demo app where you can draw with a simple paint editor on one side and it'll run the algorithm on the right side and animate it in. That's kind of my vision for that. And the library will just be powering it all underneath. Yeah. Yes, it was. Yeah, some people still refer to that as well. I think wave function collapse is a pretty good name, actually. Okay, so then I gotta implement get cell at. Not a problem. State, wave state. Cell. You know, I could make it maybe cell. Or if I implement the accept T handling that I want to implement, that'll hide that. So for now, I'm gonna write gross, disgusting code. You can laugh at me if you want. That's what I'm gonna do. So let's get the grid. Wave state grid. And then we can case match on the get cell. Whatever it was. Something. If just cell. And then we'll just do pure cell. Here we're going to do error. Fix me. Get cell at. Yeah, kind of like an almost like a formal grammar type of thing. I characterize it as a forward constraint propagation solver. Like you can almost look at constraint propagation solver like forward propagation constraint solving. The main part of the algorithm is doing that. And there's quite a few algorithms on that as well. And quite a few refinements on how to make that fast. Let's see here. Okay. The function that I want for this whole is defined. There's a grid cell. Cell. I could do. Cell app. Okay, good. Jump over there. Cell at. Cell X grid. Okay, let's see. Test runner's good. We all compile, we're good. Okay. Okay, so choose cell at. Alright. So then we can use is collapsed at. Find that one pretty easy. Cell X. And then we can get the cell from get cell at cell X. And then we can do pure collapsed cell. Okay. And then we can get to propagate back to propagate collapse. We have our choose cell action here. We don't have to do that here. We probably should get the cell and the cell index here. Okay, because I think we need to, after we collapsing, we gotta propagate the choice. That cell out to neighbors, sort of figure out all that. So I think we're going to end up needing propagate steps, some kind of stack of cells to propagate to. Let's get the cell, choose cell. Okay, so we choose it, we got to collapse it. I think we have that one, collapse at. Yeah, so this should be cell X. Collapse at. And then we got to propagate. The choice of that cell out to neighbors across the wave. Okay, so this is the tricky part here, but we're getting to the end of the stream, so we're gonna have to call it here. Propagation. We'll implement propagation next week. Looks like we don't need the wave state yet. Yeah, so fuse cell does return the index. That's good. Indeed good. Yes, yes, yes. Okay, let's review our code. Right, so we changed entropy cell to be the index, the heap to keep the index list. The cell index, that's the one. Entropy list, entropy cell index list. Yeah, they're super cool. They really are. I first encountered them, gosh, ages ago. I gave a talk at PyCon in like 2014 or 2015, somewhere around there, on using it for level design. And so like generating random dungeon levels. You can use constraint solvers to like have a bunch of rules that say like, okay, well, there has to be a boss-like enemy within one room of the exit, and the player has to be in the start room. There can't be any monsters in the start room. There's got to be a health potion in some room between the boss and the player. That kind of stuff. And you can kind of define all those rules, and then it'll keep generating levels until you get one that solves the constraints. And yeah, they're pretty cool. Also, a way to solve Sudoku as well. Maybe, I don't know, maybe could be an efficient way. I'm not the most efficient way, maybe, but yeah, they're pretty neat, quite useful. Okay, yeah, so we changed the heap elements type. We added, so in order to implement propagate collapse, we had to like kind of change some of our accessors into the state to use cell indices so that we don't keep copies of cells everywhere. Saw Reba applies at Sudoku, 100 milliseconds, yeah, pretty fast. Yeah, there was one, so I gotta go back over it, but there was one, speaking of Sudoku solvers, there was one in Bird's book on functional pearls that, like, I don't quite understand, but it does it in a very neat way. That isn't constraint solving. Yeah, consider it alternative to search, sort of like when you make a decision along the way, you throw out all the other possible branches as you go along, kind of like tree pruning, if you've ever done a chess engine. Only a little bit different because you're not cutting off whole branches, you're propagating those changes out to the whole state space. So yeah, sort of similar type stuff. Is collapsed at, yeah, so we implemented a few helper functions here on this round, and a little progress on the main algorithm. So yeah, I think next week we'll be ready to go on the main propagation part. Take a stab at it. Okay, let's get that. Okay, let's rebase here. I don't want to diff. Yes. Sorry. Rebase. Right. Interactively. We'll squash this one up here. Reword this one. Here. We implemented about half. No, not even a quarter. Just have to propagate. Cool. And there we go. Let's push that up. So, if you're tuning in for the first time, the code that you've seen here tonight is on my GitHub. I'm Agent Ultra. And you can find it at Wave Function Collapse. Paste the link there. Copy. Now. Okay. So there it is. That's the code for this project. And you can star, like, fork, whatever you want. Learn. And try to take it the rest of the way on your own. Who knows? Yeah, so if this is your first time tuning in, welcome. Thank you for watching. It was nice having you. I do these streams once a week, usually on Tuesday evenings at about 10 after 8 in the Eastern Standard Time Zone. So if you want to write that down, or if you're on the Twitch anyway, you can, like, you know, follow and you can set up your notifications. You'll get notified when I go online. And check my sketch. If you're watching in a different time zone, of course, follow me on the Mastodons in the Petaverse. I'm on typestop.pl at Agent Ultra. It's web at Agent Ultra, which has all my links to all my other stuff. But I've got a YouTube channel there as well where I kind of back up my streams, so you can follow along there. And there you go. So give us a like and subscribe there as well. It really helps. Lets me know people are watching and enjoying. You know what I'm saying? And follow me here too, because I update frequently on what I'm up to and stuff like that. So yeah. Go to the link above, of course, declarative.tv. That's a website with other cool streamers who are doing things in other declarative style languages, including functional programming languages like Haskell. And there's also a channel on that Discord server that's linked on that site above. You can go to and chat with me between streams and talk about your projects and whatever. Questions you wanted to ask but didn't want to do it on stream or forgot or thought of later. That sort of stuff. That's it. That's all I got. So thanks for tuning in. May all your monads be free and your types always check. And hopefully we'll see you next week. Take care out there and happy hacking. Alrighty. End of stream.